So this was the problem. Find the maximum value of z is equal to 2 twice of x1 plus thrice of x2, subject to x1 plus x2 less than or equal to 30, x2 is greater than or equal to 3, x2 less than or equal to 12, x1 minus x2 is greater than or equal to 0. Here there was a printing mistake in this problem. The sign here it is greater than or equal to. The numerical that I have given you is in that particular case there is less than or equal to sign to be taken into that was given, right? The fourth constraint is same, that is 0 is less than or equal to x1 less than or equal to 20, right? So this were the constraints, and the problem appears to be very straightforward problem. But what is the trick that is to be remembered in this problem that I'll be sharing with you, right? So when we have this particular we started with we'll be considering our first constraint here, which is x1 plus x2 is less than or equal to 30. We'll be neglecting this inequality sign. As now we are neglecting the inequality sign, what will happen? X1 plus x2 will be equal to 30. If you put x1 is equal to 0, the value of x2 comes out to be 30. We get first point for this constraint line as 0 comma 30, right? If we put x2 value into it, x2 value as 0 into it, we get the value of x1 is 30, and hence we get another point for this constraint line, that is 30 comma 0, right? Now the another constraint, the second constraint that we have is x2 is greater than or equal to 3, right? So again here we are going to neglect the inequality sign, and hence we get this particular constraint as x2 is equal to 3 only, right? Similarly, we have another constraint in which we have another constraint which is given as x2 is less than or equal to 12. Here we can neglect the inequality sign, and we get the constraint line point as x2 is equal to 12. Now, the another constraint that we have is x1 minus x2 should be greater than or equal to 0. Now, this is very, now this particular line is just a line like a calibration line, right? So, if we neglect the inequality, what it becomes is x1 minus x2 is equal to 0. So, that is x1 is equal to 0. So, for any value of x1, the value of x2 remains same, right? So, this particular line will be what? It will be line passing through the origin at an angle 45 degree with both the axes, right? So with respect to both the axes, it will have a 45 degree. So this particular constraint is now very important, and it is to be handled in a proper way. Particularly there is a chances that the mistake can happen in this particular constraint. Again, we have another constraint here, that is 0 is less than equal to x1, and x1 should be less than or equal to 20. So 0 is no 0 is sorry greater than or equal to x1. So 0 is greater than or equal to x1 matlab kya? X1 should be in your first quadrant. That is understood. Again here they are saying that x1 should be less than or equal to 20. So this particular we can neglect the inequality sign here, and we get equation as x1 is equal to 20. Now let's plot this inequality no, constraint lines or inequality lines on your graph, right? So this is my first no, this is my x1 and x2 uh, axis. Okay, I forgot to write the names of the axis here, but it's okay, right? So this is the first quadrant that I've got. The maximum coordinate for x1 and x2 is 30. So accordingly, you can draw the line of the axis. Now, the 30 comma 30 line, right? So this is your x1 plus x2 is less than or equal to 30. Less than or equal to 30 means the area below, less than inequality means that the area below the line is to be considered. So hence the arrow mark that has been shown is below this constraint line, right? Now we have another constraint line which was x1 should be greater than or equal to 20. So the coordinate become x1 is equal to 20. So the x1 is equal to 20 constraint line is also here. We had another constraint where x2 was greater than or equal to 30. Right now, here also for x1 is equal to 20, if you see the inequality sign, it is less than or equal to. So the region which is no what we can say, below this line is to be taken into consideration. If we see, if we take this side region, opposite side, what I have denoted with this particular arrow, what will happen, the x1 values will be more than 20, and that is not acceptable because x1 is less than or equal to 20. Similarly, x2 is greater than or equal to 3. So for this, the point happens to be x2 is equal to 3, and as the x2 value should exceed or should be equal to 3, the arrow mark that I have given is the upward arrow mark here, right? Similarly, for x2 is less than or equal to 12, what it suggests that the x2 value should be, no, it can be 12 or it can be less than 12. So this is the constraint line for this equation, and the arrow mark that has been shown is in the downward side. Now what is the important, now here we have drawn the x1 comma x1 minus x2 greater than or equal to 0 constraint line, which passes through the origin and has 45-degree with both x and y axis, or for x1 and x2 axis. Now what is important here, what is the difference in this particular problem is that I have written here. Now for the normal equations, greater than or equal to sign suggests the region above the constraint line is to be taken into consideration, right? And for the no, for less than or equal to sign, the region below the constraint line is to be taken into consideration. So that is important, right? Now, but what happens is, this is the normal philosophy what we nor no we follow. But for this type of equation, right, this type means only this type, right? X1 minus x2 greater than or equal to 0. If this particular type of constraint is given to us, here we will have to go in the reverse manner, right? Only for this particular equation. I'm not telling for the equations which are other than this. Only for this x1 minus x2 which is greater than or equal to 0, you'll have to consider the region that is below the constraint line, and here x1 minus x2 greater than or equal to 0, we'll have to consider the region above the constraint line. Now what I'm telling to you is, no, this is not only restricted to this numerical, it is applicable for all the numerical. So if any the further numerical, if we have that in some different numerical, if I have x1 minus x2 is greater than or equal to 0, that in that particular numerical also I'll have to consider the region below the constraint line also, or vice versa. If it is less than or equal to 0, I'll have to consider the region above the constraint line, right? So that is to be taken into consideration. Now this somewhere you make a note of this. I'll be providing you the PDF, right? But again, your handwritten notes and something that that has passed through your hand is, that gets remembered. So that particular, now this is to be remembered, so I made a square here. So other, now here the sign is greater than or equal to for 0 for this equation, but the region that is to be considered is below this particular line. ठीक है. So now if all the constraint line, if I'll have to find out the area which is satisfying all these constraints, so this happens to be the hashed portion appears, this happens to be the feasible region. So here the feasible region is A, B, C, D, right? So this is the feasible region, and as you all know the definition of what is a feasible region. So feasible region is that region which satisfies the all the constraints, right? So any point in this feasible region can act as a, what it can act as a solution, optimal solution for this particular problem. Now according to the extrema point enumeration approach that we are, so no, that we have considered, what does this extrema point enumeration approach tells us is that the optimal solution will be lying on the any one of the vertex, right? So I have A, B, C, D as my vertex points. Even this particular point I forgot to know, this particular point is D, and this happens to E. So again I'll be making change and I'll be sending it to you, right? So this particularly is A, B, C. Then I have this I have this D point here and E point here, right? So just a correction here. This is a D point here at the intersection, and at this point D, it is the E point here, right? So if I'm no, if I have to find out the coordinates, I can find out the coordinates. For A, it is pretty straightforward. For B, no, it is no. For B, you'll have to take into consideration the lines which are getting intersected. So here, x2 is less than or equal to 12, and x1 minus x2 is greater than or equal to 0. Lines get intersected at point B, and with the help of these two equations, we can find out what is the coordinate of point B. It comes out to be 12, 12. Similarly, for line C, it is an intersection of x1 plus x2 is less than or equal to 30, and this line which is x2, it is less than or equal to 12. So even this particular point can be found out. The coordinates of this point can be found out. Similarly, I can find out the coordinate of D point here, which is an intersection of x1 plus x2 less than or equal to 30, and x2 is less than or equal to 20. So that is there. And for for E point, what we have, E point is an intersection of x2 greater than or equal to 3 and x1 less than or equal to 20. So accordingly, I can find out all these coordinates, and if I find out the value of the objective function across all these points, so z at A is equal to 15, z at B is equal to 60, z at C is equal to 72, z at D is equal to 70, and z at E is equal to 49. So if we see our objective function, it was maximized, right? And if we see at which point we are getting the maximum value appears, it appears at C is equal to 72, right? So here the Z at C is equal to 72 is equal to Z max for x1 is equal to 18 and x2 is equal to 12. Now the numerical was pretty straightforward, but only the what we can say, the point that needs to be understood, or why this problem is special, is that it has a constant x1 minus x2 is less than or equal to 0 or greater than or equal to 0. So if that is the case, we'll have to be very alert at that particular time, and we'll have to take this that this particular box what I've written into this box into consideration, and that will help you to get the right answer, right? I'm hoping that you all have understood this problem, and what was the change that you need to consider is that has been understood, right? Similarly, let's take another problem now, which is one of the uh, no, problem which can develop your understanding regarding this graphical method in a more proper fashion, right? So we have a very simple numerical, that is maximize z is equal to x1 minus x1 plus x2 2x2 subject to x1 minus x2 less than or equal to minus 1, and we have another concept as minus point x1 plus x2 should be less than or equal to 2, x1 comma x2 greater than or equal to 0. Now I'm going to tell you a very very important no, thing here. When you see a numerical and when you specifically see the constraints, so on the constraints, what should have constraint has LHS side and RHS side. LHS मतलब left hand side, एंड आरएचएस मतलब क्या, आपका राइट हैंड साइड. तो इनइक्वलिटी का इधर का आपका जो इक्वेशन होगा वो आपका एलएचएस होगा, इनइक्वलिटी के बाद का जो वैल्यू होगा आपका आरएचएस होगा, राइट. अभी आर कोई भी कंस्टेंट अगर हम लोग लेंगे तो आरएचएस में आपका नेगेटिव साइन कभी भी नहीं आना चाहिए, ठीक है. ये आरएचएस में ये नेगेटिव साइन हमको नहीं चाहिए, ठीक है. तो आरएचएस में अगर हमको ये नेगेटिव साइन नहीं चाहिए तो हमको क्या करना पड़ेगा, विल हैव टू मल्टीप्लाई all these complete constraint by -1. So I have written here only, considering the constraint x1 minus x2 which is less than or equal to -1, the constraint has a negative sign on your RHS, that is the right hand side, which is not acceptable, right? So multiplying the above constraint by -1 on both these sides, we'll have to multiply it by -1 on both these sides. So if we multiply it by -1, what happens is that we get x1 minus x1 plus x2 Now this inequality sign, which was earlier less than or equal to, will now change to greater than or equal to. Okay, this is also the change that will have to taken into, that is taken into consideration. So not only minus sign, no, not only multiplication by -1 on both sides, even the inequality sign is to be, no, it is to be made opposite. So here what will happen is that the constraint now that gets formed is minus x1 plus x2 should be greater than or equal to 1. Right, now that we have got this, now here you can see that the RHS is without a negative sign. You can have a negative sign in LHS as many times, it doesn't matter, but in RHS particularly
काय
cannot have the
कोणाचं
minus sign. Any doubt?
नैना काकूचं हा
Rutuja, I guess it is your voice, you can mute your mic. Okay, let's proceed. Minus x1 plus x2 should be greater than or equal to 1. So this is the constraint that we have got. Uh, Neglecting the inequality sign, what we can do is, we get an equation minus x1 plus x2 is equal to 1. So if we put x1 is equal to 0, we get x2 is equal to 1. So we get our first point as 0 comma 1. We get no If we put x2 is equal to 0, we get x1 is equal to -1, and we get another point for this constraint line as -1 comma 0. Right, so this is the these are the 2 points that we get for our constraint line. Now let's take another constraint. Here you can see there is a negative sign in the LHS side, but no, as told earlier, as many as negative signs can come at your LHS side, but no, there shouldn't be a negative sign to the value on the RHS of the constraint. So considering the constraint minus 0.5 x1 plus x2 is less than or equal to 2, we can neglect this inequality sign, and the constant that we get is minus point x1 plus x2 is equal to 2. So you can put x1 is equal to 0, therefore x2 is equal to 2. Right, so you get 0 comma 2 here. You again have put x2, no, if you put x2 is equal to 0, you get x1 as minus 4 comma 0. So getting the answer in this particular fashion, it is, very simple to get. Now here you can see, when we are finding out the points, what may happen is that you may get a negative point, it doesn't matter. What should happen is that you have the feasible region should fall into where it should fall in the first quadrant. So the non-negativity constraint should get fulfilled. Okay, so that is important. You don't get panic if you are getting the x1 and x2 values as no, as a negative value. Finally, when you have to identify visible region, that should fall into your uh, non-negativity quadrant, which is your first quadrant, right? So when we solve this numerical further, what will happen is that I've written here the feasible region is shaded and forms a polygon ABC. Coordinate of A are 0, 1, B is 0, 2. Point C is the intersection of line minus x1 plus x2 is equal to 1 and minus 0.5 x1 plus x2 is equal to 2. So if we solve this here, we get the coordinates as 2 comma 3, right? So here what is going to happen is that if we find out the values of z at all the points, the coordinates here, so here you get z at a is equal to 2, z at b is equal to 4, and z at c is equal to 4. Now here you can see why I've taken this numerical. Okay, the very first thing that I wanted to explain while taking this numerical was the minus sign is not acceptable on the right hand side of the constraint. Make it a note somewhere that this minus sign is not accepted on the right hand side. And the another thing is, now we have got a solution. We have to decide a solution now, whether z at b is to be max, z at b is no, to be considered as the optimal point, or z at c is to be considered as an optimal point. So that is now to be taken into account, because our maximum value is coming at 4 and 4 for both z at b and z at c. So what happens is that the also the line joining the B and C, every point on the line joining B and C will have the Z as 4 only. So how the solution of this particular problem is to be written? Now this problem is a special case in which there is not a single optimal solution. There are multiple optimal solution which has the Z max value as 4, right? So point B and C give the same maximum value as Z is equal to 4. Also the points between B and C on the line BC will also give the value Z is equal to 4. Therefore, the problem has a multiple optimal solution and your Z max value comes out to be 4. In the numericals that we have seen up till now, the Z max value was not getting repeated, right? Or even your Z values are not getting repeated. But in this particular case, the Z values got repeated, and all the repeated values are only the Z max values, right? So what is this particular type of numerical doesn't have a single optimal solution. It has a multiple optimal solutions, right? So you can take any, you can have a B point as an optimal solution. Even the C point can be taken as an optimal solution, or any point which is on the line B and C can be taken as an optimal solution, right? So this is very, very, very important. Such numericals can be asked in the examination, even if they are not no, asked in the examination, doesn't matter, but your understanding should be, it should be uh, perfect, or you should understand the solution in a good fashion, right? So let's move ahead and see another case here. Okay, so I'll be enlarging this, and the solution will be in your. Okay, so we have a problem. Maximize z is equal to 3x plus 2y, which is subjected to minus 2x plus 3y less than or equal to 9. 3x minus 2y, which is less than or equal to minus 20, and here x and y should be greater than or equal to 0, right? Now you shouldn't be getting panicked if you see the numerical. Here also it is a two variable numerical only. Now otherwise you will be getting confused. Keep sir has taken the numericals of x1 and x2 in our class, and how come this x and y has come into this question paper, and this is out of this syllabus? No, this is x and y happens to be the two variables, so it is a two variable LPP problem which can be solved with the help of the graphical method. So there are two variables here. Now if you see the first constant, very straightforward, minus 2x plus 3y is equal to 9. If you put the value of x is equal to 0, you'll be getting the coordinates at 0 comma 3. If you put y is equal to 0, you'll be getting the coordinate as minus 4.5 comma 0. Now here if you consider the second no constant, here you have a negative sign. So if I'm having a negative sign, I already told you we'll have to multiply it with the minus 1 on both the side, and even the constant inequality sign will get changed. So what we have is minus 3x plus 2y uh, greater than or equal to 20. So we can neglect the inequality sign. We can put x is equal to 0, so we get y is equal to 10. So the first point appears to be 0 comma 10. Nextly, the by putting y is equal to 0, we get a another point which is minus 6.67 comma 0. Now if we try to draw the solution of this problem in the graph, so let me make it zoom out for you all. Okay, so here you can see the first constant line, which was your minus 2x plus 3y is less than or equal to 9. So here the point is 0 comma 3 and minus 4.5 comma 0. The I've drawn the line as the constraint is less than or equal to 9, so I'll have to mark the area which is below this particular line. For the another constant that I have, it is minus 3x plus 2y is greater than or equal to 20. So I have my first point as 0 comma 10, another point as minus 6.67 comma 0. I can draw a line here, and the constant is the inequality sign is greater than or equal to 0. So the line, the area above this line is to be taken into consideration. Now, if I have to go and find out what is the feasible region, so now here the feasible region is not actually available. The hashed portion that I have no, told you, or I have the hash portion I have marked here, are only with respect to that particular constraint line, right? So there is no overlapping of the feasible region of these two constraint lines that are happening. So what is this? As the feasible region do not overlap, the problem has an infeasible solution. That is very, very important. You won't be getting an optimal solution for this particular type of problem because you don't get a no, you don't get a feasible region only. So the problem has a infeasible solution that is to be written, right? So this, this is should be understood. Now, such problems, may have, particularly according to the graphical method, we can say the problem has infeasible solution. But if we go with find out with a normal way that we do for LPP, that is simplex problem, this problem may have a solution. I'm telling may have a solution, right? So particularly you can get a solution, you can even not get a solution. But now that we have been told that solid graphically, so according to the graphical method, this particular problem no, do not have a feasible solution. So this problem has a infeasible solution. That is to be written properly. Now let's take another very simple numerical. Okay. Now again, be alert. Take your pen and paper, and we'll be solving this numerical together. Right. So we have our first constraint line as x1 minus x2 is greater than or equal to 0. We have so considering the first constraint, x1 minus x2 is greater than or equal to 0. So if you neglect the inequality sign, it is no, x1 is equal to 0, and this line passes through the origin at an angle of 45 degrees. So something should click into your mind now that the constraint is x1 minus x2 is greater than or equal to 0. So now if that is case, which is the region that needs to be considered, we have already discussed, right? If x1 minus x2 is greater than or equal to 0, so the area that is below the constraint line is to be taken into consideration. That should be, no, it should be very clear in your mind. Right. Now let's move towards our next this thing, that is we have next constraint as 2.5 x1 minus x2 is less than or equal to minus 3, right? So here again minus sign is coming, so you'll have to convert it into the no you'll have to make this minus sign disappear. So you'll be multiplying it entire both the sides by minus 1. So minus 2.5 x1 minus x2 should be लेस देन और इक्वल टू -3. तो यहाँ पे -2.5x1 आएगा प्लस x2 आएगा, ये वाला इनइक्वलिटी साइन ग्रेटर देन और इक्वल टू हो जाएगा और ये 3 हो जाएगा. तो यहाँ पे आप लोग यू कैन सी दैट पर्टिकुलर इक्वेशन here written here. So if I put x1 is equal to 0, x2 comes out to be 3, I get a point as 0,3, and if I put x2 is equal to 0, I get no, another point that that is x1 is equal to -1.2, and I can draw -1.2, 0 points that I have got. So okay, so now somewhere this
Yes,
line will
sir.
meet, right? And that is your feasible region that you will be getting, right? Now what is important here? The feasible region is shown shaded. Any point within this region satisfies both of your constant. X1 minus x2 is greater than or equal to 0, and you have another constant that is minus 2.5 x1 plus x2 greater than or equal to 9, right? So greater than or equal to 3. But none of the points satisfies the non-negativity criteria. यहाँ का none of the point in this feasible region is going to satisfy your non-negativity criteria. Therefore, the problem does not possess a feasible solution. That is to be written very clearly and bluntly.